Have you ever thought about how we collect energy from the sun? In this presentation, we will give a brief overview of how the study of UV-vis absorption through the knowledge of quantum mechanics can help us harness rays of light produced by the sun for energy purposes.
UV-vis absorption in materials is accomplished by the interaction of light with the valence electrons in the material. Incident light is absorbed by the electrons, which causes them to be excited to higher energy states. The difference in energy between the electron's ground state and excited state is necessarily equal to the amount of energy taken from the incident photons. Thus, in order for an electron to be promoted to a specific state, the incident photon must have an energy greater than or equal to the difference between the electron states. As shown in Figure 1, the electron will increase energy proportional to the energy of the incident light. The amount of energy increase is discrete and can be quantized. In regards to organic chemistry, electrons can transition between sigma, non-bonding, and pi orbitals, and between bonding and anti-bonding orbitals, which can change the stability of the molecule. This is also shown in Figure 1. Similar to organic chemistry, metals also undergo transitions when energy is added to the system. The transition between orbitals is caused by the energy absorbed by the material. Also, in regards to inorganic chemistry, charge transfer complexes can form when the radiation absorbed causes the transfer of an electron from a donor orbital to an acceptor orbital. Excited electrons can lose their energy by transmitting it to an oscillation about their bonds. This occurs when the atomic vibration energy is transmitted through bonds, causing local atoms to start oscillating as well. This causes a vibration cascade throughout the material. The result is the generation of a phonon, which is a vibrational wave of atoms in a lattice which is associated with atomic shifts. Phonons can be considered quasi-particles. Phonons are similar to photons in that they contain packets of energy. A photon differs from a phonon in that it is a quanta of electromagnetic radiation, not vibration. While photon energy is given by h nu, or Planck's constant times the frequency of the photon, a phonon's energy is given by h omega, or Planck's constant times the frequency of the phonon. Similar to the behavior of electrons, phonons exist at quantized energy levels, as shown by the figure. Phonons can be promoted from one energy state to another by absorbing the energy difference between the states, from either an electron or another phonon. As shown in the figure, phonons can act as particles traveling through an object. As they go through a particular region of the object, they cause the local atoms to be displaced from their equilibrium positions, increasing the energy of that area. For this reason, phonons can play a large role in thermal conductivity. The thermodynamic properties of a solid are directly related to the structure of phonons in the material. Specifically, the density of states determines the heat capacity of a crystal. Energy fluctuations that occur naturally in a lattice at a non-zero temperature. These vibrations are caused by phonons. Furthermore, random motion of atoms in the lattice is what is usually thought of as heat. These phonons are generated by the thermal energy of the lattice and can carry that energy throughout the lattice. This is similar to dominoes falling over. As stated previously, phonons play a direct role in the thermodynamics of a solid. As the temperature of the solid is raised, the amplitude of the phonons increases, causing the energy to be sent through the whole crystal structure. The speed in which the phonons transfer heat is given by the thermal conductivity equation as shown in the slide. Thermal conductivity, kappa, is equal to the specific heat of the material multiplied by the mean free path traveled by the phonon multiplied by the velocity of the phonon. The product is then divided by 3. This is a formulaic approach to showing how phonons have an effect and ultimately determine the thermodynamics of a solid. Though phonons explain heat conduction through non-metal materials, surface plasmons explain heat transfer in metals. Surface plasmons generate heat conduction through collective oscillations of conduction electrons from the metal particles embedded in a dielectric matrix. Plasmon generation and propagation through photon absorption requires an additional step, however. A prism is needed to align the wave vector of the incident light
with the wave vector of the plasmon. This is shown in the figure. A Kretschmann setup uses a prism that is in direct contact with the metal surface. The prism aligns the incident beam, facilitating the generation of a surface plasmon. This is different than other setups in which there is a pocket of air between the prism and the metal surface, but that schematic induces other variables such as the passage of energy through the air pocket that can confound the results.
As plasmons propagate through the material, they can interact with and transfer energy to phonons in the lattice. In this way, the energy of incident phonons is converted to thermal energy. The energy of plasmons can be quantified by the following equation. The energy of the plasmon is equal to the reduced Planck's constant multiplied by the square root of the conduction electron density times the square of the elementary charge divided by the product of the mass of an electron and the permittivity of free space. This can be simplified to the reduced Planck's constant multiplied by the plasmon frequency.
As we have shown so far, surface plasmons and phonons contribute to the transition of light energy into thermal energy in a material. How does this knowledge transfer to a practical application? What can we do with what we have learned so far? UV-Vis absorption mechanisms are important to the field of renewable energy because they form the basis for solar selective coatings. Solar selective coatings are a thin layer of material that can be applied to a solar panel. The coatings are designed such that they will absorb the highest possible percentage of solar radiation and emit the least amount of waste energy possible. The thermal energy collected by solar selective coatings can be used for power generation. An example of this power generation mechanism is a power tower. Power towers use reflective panels to concentrate light at the apex of the tower. A solar selective coating will capture that energy and transmit it to a fluid that can be used to drive a turbine.
A black body is an idealized physical material that absorbs all incident electromagnetic radiation. Frequency of light as well as angle of incidence can be disregarded. A black body is held as a standard for any light absorption material. A black body spectrum is the amount of energy a black body will emit at a given temperature. In this case, the sun is about 5,000 degrees Celsius. This means that the spectrum of light emitted, thus absorbed by the Earth, is in the ultraviolet, visible, and near-infrared portions of the spectrum. This would mean an ideal solar selective absorber would primarily absorb wavelengths less than 1250 nanometers. The spectrum of the sun is shown in the figure. The black line is the idealized spectrum of a black body at the temperature of the sun. The yellow region is the solar output that reaches the atmosphere of the Earth, and the red region of the figure is the portion of the solar spectrum that reaches the surface of the Earth. The difference between the yellow and red regions is the energy absorbed by the molecules in the atmosphere. As shown in the figure, the majority of the solar radiation is in the ultraviolet and visible ranges of the spectrum, with a fall-off in output further into the infrared region. It is important to note that as the temperature of a black body decreases, the primary energy output shifts towards the infrared. So objects on the Earth tend to radiate primarily in the infrared region of the spectrum. Thus, the ideal solar selective coating has a high absorbance in the UV-Vis region and zero emittance above 1250 nanometers.
By understanding both phonons and surface plasmons, efficient and complex solar selective coatings can be made. This understanding enables researchers to pair the best metals with the best non-metal materials to facilitate the creation of the most efficient solar selective coatings. This can pave the way for a new form of renewable energy.
In the end, this is an important step towards renewable energy and optimizing solar power. So an understanding of these principles is crucial to engineering the most efficient solar selective coating to create the most efficient energy producer.